Hi scientists! Welcome back to Miss Banks' Inquiry Learning Science Lab. Today I want to talk about something that I've been thinking a lot about. Time. So I think about time a lot. There's time passing, there's time happening. Time is flying by all the time. See what I did there? But when I think about time, I often think about clocks. Specifically those clocks that go tick, tock, tick, tock, tick, tock. You know what I'm saying. Those are grandfather clocks, and they have a little rod in them that moves back and forth, then back and forth, helping count how many seconds are in a minute, how many minutes are in an hour. You get the gist. So today I want to talk about pendulums. Pendulums are that little bar that go back and forth. And I want to test what affects the amount of times pendulums go back and forth in a minute. We're going to find out today. But before we start, make sure we have all of our safety measures in place. Lab coats on, hair tied back or put up, closed-toed shoes, and of course, your safety goggles. Let's get started. Teachers, did you think I forgot about you? Of course not. So, when we're setting up this lesson, we need to engage our students. So how I would start this lesson would be by first showing a video of a grandfather clock. It might seem obvious, like every student would know what that was, but some might not, and we want to make sure everyone has the same shared mental image before we begin. I would then supplement it with another example video, these are super short, of a metronome, and explain to students that metronomes also go back and forth and back and forth and back and forth and help musicians stay on the beat and have their beats per minute. It all kind of relates to one another. So that's how I would engage the students. Then, to set this lesson up, I would do it in kind of like a stations format where there would be three main areas of inquiry learning, because in our experiment today, we'll be doing three trials. Three stations, one where students are changing the length of the string on the pendulum, one where they're changing the weight, so how heavy it is with the amount of washers, and then there will be one station where students are affecting how far of a distance they drop it from to see how it goes back and forth. So those would be three different stations, and ideally students would work in teams of 2 or 3 paired together. So when you make these stations, the students will be pretty much independently going around, and they'll have their science experiment packets to go with this. But just note, when you teach this lesson, students should have already had some lessons and like basic knowledge of how to conduct an experiment. There should be a knowledge already had and kind of like claimed of what independent variables are, dependent variables, what your constants in an experiment are, and what it looks like to fill out a table and a graph. So this would ideally fall kind of like after this has been introduced. This would not be the unit you're introducing these concepts, but there's definitely time for reviewing, which would always be recommended. So I'll get into more details of what this is actually going to look like in a second, but these are the important ways that you get set up. All right, scientists, so you're probably wondering what the experiment is today. Let's find out. So first, I have my experimentation packet here that my teacher would have provided me with. In this case, I made my own. So this experiment packet asks our inquiry question, which is, what variable affects the amount of swings a pendulum has per minute? So what makes the pendulum go back and forth and back and forth a certain time per 60 seconds or 1 minute? So we have a review of our vocab on here, the independent, dependent, and constant, and then our supplies, which your teacher should already have set up around the room in your stations. So today we'll be testing 3 different independent variables. We'll be testing the length of the string on the pendulum. We'll be testing the amount of washers, which creates a heavier weight on the pendulum. And then the distance which you're releasing the pendulum from, which will have a ruler set up and release. So as we go through these experimentation stations, you'll be filling out your packet with your IV and your DV, depending on which station you start out, will depend on which trial you have. Then you'll fill out your table with your data, and you'll fill out your graph. This will come in handy later, and here's a closer look. first station that we're experimenting at is testing what the effect of number of washers, or the weight, is on the amount of swings per minute. So I'm going to walk you through how to fill out your packet for this first one, which will be how you collect your data, which will later turn into evidence, the most important thing in having scientific inquiry and conversation. So let's get started. So when we begin, we identify our IV, our independent variable. That's the thing that's changing. So in this one, what is changing is the number of washers. And our DV, or our dependent variable, is going to be the number of swings per minute. So once you identify that, you can ask your inquiry question. So what is the effect of the number of washers on the number of swings per minute? And you'll put your IV and your DV here in this table. We'll fill these out when we start experimenting. And on your table, you'll want to put the effect of number of washers on number of swings per minute. So your independent variable will go down here. So we'll have number of washers. And then we'll flip on over to put the number of swings per minute. And we determine our scale after we collect our data up here. So let's get experimenting. Okay, so the way your experimentation station will be set up when you arrive is your teacher will have a pencil taped to the edge of a surface or a table or a desk, whatever your classroom looks like, with your string at 8 inches, that's our constant, and it'll have a paper clip with 2 washers, which is our constant weight. So for this experiment, we'll be changing how many washers we have. So this is round 1. So what you're gonna do when you get here is take your washer by the top, bring it all the way to the top, and then release. When you count, you wanna make sure it goes back and forth. That's 1. Back and forth. That's 2. So that's how you'll count. But don't forget to start your timer before you begin your experiment. All right, let's go. Okay, we're now moving on to our next experimentation station. So at this station, we'll be testing the pendulum to see how the distance released impacts the number of swings per minute. So I have my chart here all filled out. So you can see my independent variable is the distance released. My dependent is the number of swings per minute. I have that written into my inquiry question. I have it on my table, and I have my graph all labeled. All right, let's see what our results are. All right, so for this station, we're gonna need our ruler, and we'll go back to our constant with our same 8-inch string and our 2 washers. So you can see we have our pencil lined up, and your teacher will have this ready at 6. So for the first experiment, or the first trial, we're gonna move our ruler to create a straight edge, 1, 2 inches. So when we release, we'll move it over to the edge of the ruler and do that. For our second, we'll go over 1, 2, so now we're at 4 inches. We'll move and release. And then for our third, we'll go 2 more inches. So now we're at 6, and we'll release. We'll do all of these for 1 minute. All right, let's get started and see how it goes. Okay, it's time for our final experimentation station. So at this station, we will be testing the length of the string on the number of swings per minute. So once again, I have my table all filled out. So my independent variable is the length of the string, so that'll be in inches. Then my dependent is the number of swings per minute. I have my table filled out, my graph labeled. Always remember to include your unit of measurement, and let's see what it looks like. Okay, so at this final station, your teacher will have 3 pencils set up. Now you'll notice, whoop, the string is at different lengths. So we have our 4-inch, our constant, which is our 8-inch, and then we have our 12-inch. So we'll take turns releasing them just from the very top, and we'll see how they differ. All right, let's get started. All right, scientists, last one. Now we're at our 12-inch string. So remember, bring it to the top, and let's see what happens. Okay, scientists, we have now gone through all 3 of our experimentation stations. So at this point, we'll all return back to our desks and look over and interpret our data that we've collected. So in our experimentation station packet, we have a set of questions at the back. These questions ask things of the students like, which trial looks different than the others? Can you label which independent variable made the biggest difference on the dependent variable? What do you think would happen if we kept this experiment going? We want to get students in the mindset of looking at their data that they collected and examining it and using that as evidence to make predictions for what we think can happen next. Because in science, the most important thing to teach our students is that we never really have a concrete answer. We're gathering evidence, not facts, evidence to help answer these inquiry-based questions that we have. So when your students go through their data, they should see that the number of washers didn't really do anything, just kept a straight line. The distance released, same thing, straight line. However, when you change the length of your string, whoop, we go down, so it decreases. So you can explain to students that this is a physics topic that happens due to the amount of gravity on the length, where it's coming from. It might be a little bit complex for the age group that I would imagine this would be taught for. I would think this might be ideal for like a 3rd grade classroom, just due to the different parts, the moving parts of the experiment and all that. The really big takeaway of this concept is that you're collecting this data, you're changing the variables. So you're changing how long that string is or how many washers, and you're graphing it. You're seeing from your table, from your initial question, the differences between the graphs. Students should be able to look at these and be like, oh, this one looks a little bit different. So you're seeing that there's more force, which is slowing it down because it's going from a larger distance. But the main takeaway from this is that from our experimentation stations, we collected data, which we added to our table, and we were able to prove that this would go down. So a student could answer a question like, what do you think would happen if the experiment kept going? They could say, well, I think if we had a string that was, say, 16 inches, it might go down to only swinging around 40 to 30 times, and so on. You're showing that with your scientific data, you can start to predict how things in the world work. And that's what scientists do in the real world every day. We want to show students that your experimentation is what gets us those answers. So this hopefully will connect and explain how pendulums work, how this force happens. This would go into a physics unit. This could go into an experimentation unit. I'll get into the standards in just a second, but it's really just an exciting hands-on way for students to be asking questions, getting their hands like really involved, taking data, interpreting their own data, and creating science. So that is how you go through the experimentation stations. Okay, teachers, we've made it to the final step of this project, and that is connecting it to your next generation science standards. So I've identified 3 standards that I think that this activity could work with. The third one is really like the money standard, but I'll go over the other 2 as well. So the first one is K-PS2-1, which is plan and conduct an investigation to compare the effects of different strengths or different direction of pushes and pulls on the motion of an object. So that could really be utilized with like how we're changing the weight, the distance when we're dropping the pendulum and it's swinging back and forth. You could tie it into there. So the next station is, the next standard is K-PS2-2. Analyze data to determine if a design solution works as intended to change the speed or direction of an object with a push or pull. So that goes along with that graphing, the putting information in tables, and again, kind of looking at the different changing of how high you're releasing the pendulum to swing from, the weight, the length of the string, all of that affects the pull of gravity and the push and pull and how that all works. But then our money standard that I would really recommend for this inquiry learning station would be 3-PS2-2. Make observations and or measurements of an object's motion to provide evidence that a pattern can be used to predict future motion. So this perfectly correlates with this activity. So we're making the observations and measurements through our 3 trials with changing the washer/weight, changing the distance it's released from, and then most importantly, the length of the string. So we were able, through our evidence collection and graphing and everything, to notice the pattern in the length of string, which, as I mentioned earlier, then you could predict, okay, if I made the string this much longer, it would probably have this many swings. Or you could even do, if I made it shorter, it would have however many. So that's really showing students that when you collect evidence and measurement, you get, or when you collect that data, you're getting evidence, which helps you prove, quote unquote, or really just support different predictions you can make about science. And that's really what inquiry-based learning is all about. So I hope you have a lot of fun teaching this standard and that you can use some of this activity and you get to have lots of scientific fun in your classroom. Thanks!